Thank you, Lima. First, I would like to thank Misha Verbitsky and sorry. It's on, yeah. So, thank you. You're a good chair. I would like to thank Misha Verbitsky and organizers for their work on this conference, and I'm very happy to be here. It's nice to be back in Rio 20 years after I was a PhD student at the time. And my talk is about geometric structures in a old-fashioned definition given by Carton. And I will focus then on some recent results on holomorphic manifolds, complex manifolds, which are obtained in a joint work with Indranil Biswas from Tata Institute and Benjamin McKay from University College of Cork. So those are geometric structures, and the plan of this talk is the following. Carton geometries are generalizations of homogeneous spaces. So here I take some G over H, where G is a finite dimensional Lie group and H a closed subgroup in it. And the Cartan geometries will be, or Cartan connections, Cartan also called them generalized spaces, are infinitesimally modeled on G over H. So there will be some curvature here, and the curvature will be flat, it will be zero, if and only if the manifold is locally isomorphic to G over H. This somehow is a generalization of what happens when one considers Riemannian geometry as generalization of the Euclidean geometry. So you have these Riemannian structures. They are infinitesimally modeled on the Euclidean space, and when they are flat, they are locally isometric to the Euclidean space. And this generalization here is what we call the Klein geometries, in the sense that that encapsulates Euclidean geometry as an example of homogeneous space. And then I will give some results in the background of holomorphic manifolds. So let's begin with those Klein geometries and with GX structures, which are flat Cartan geometries. So the definition of Klein is the following. You think of a homogeneous space, meaning that you have a symmetry group which acts transitively on your space, and your space is just a G over H, where H is a closed subgroup in G. And I will give here examples which are in the holomorphic setting. So in this talk, I will think about G as being a complex Lie group, and H a closed subgroup in it. So somehow try to complexify all examples you have. For example, the first one, the complex Euclidean geometry, is the complexification of the Euclidean space. So think as it as being Cn with the standard non-degenerate quadratic form. So it's not a Hermitian thing, it's a complex quadratic form of maximal rank. The symmetry group is the group of Euclidean motions, which is a semi-direct product of the orthogonal group of this quadratic form with Cn acting by translations. And other examples I have in mind are the affine geometry, the projective geometry, and in fact, I think also to all those G over P, where G is a complex semi-simple Lie group and P a parabolic subgroup in it. For example, this encapsulates the projective space, flag manifolds, Grassmannians, but also these smooth quadrics in the projective space under the action of the orthogonal group. This will be the model of the flat conformal geometry in the complex setting. So somehow all these examples are nice geometries to be studied, and each of them has some Cartan geometry which is infinitesimally modeled on it. The affine geometry will have affine connections. The projective geometry will have projective connections, and the Euclidean space will have some complex quadratic form which can vary with the point. It's like complexification of a real analytic Riemannian metric. Now, when you want to endow a manifold with one of those flat geometries, you do the following. You have a manifold. Here, the manifold will be holomorphic. And it will be locally, you will find coordinates in one of those homogeneous space with the same dimension as your manifold, in such a way that the transition maps are given by restrictions of elements in G acting on open sets in G over H. Think of a complex projective structure as we have seen in some previous talks. So here, the situation is somehow rigid because all transition maps lie in some finite dimensional complex Lie group. And classically, we have two things here. If the manifold is simply connected, for example, if you look at the level of the universal covering, all those GX structures come as pullback through a local diffeomorphism from your simply connected manifold to the model. So there is only one way to endow this kind of GX structure on a simply connected manifold, is to have a globally defined map into the model X, and then you pull back. If the manifold is not simply connected, you have some obstruction to give your GX structure as a map directly defined on the manifold. This obstruction comes as a homomorphism group from the fundamental group of the manifold M into the symmetry group G of the model X. This is called the monodromy morphism. And the developing map is equivariant when the fundamental group acts on X through the monodromy morphism and on M tilde through the deck transformations. So somehow this is the picture of those flat Cartan geometries. They come with a developing map defined on the universal cover, which is equivariant with respect to some monodromy morphism. For example, this gives you some relation between your manifold and the model X. For example, if the manifold is directly simply connected, you don't need to go to the universal cover. The developing map is directly defined on the manifold M, then the image must be open. It's a local diffeomorphism, and also closed, so the image is compact. For example, a fine structure cannot live on compact, simply connected manifolds. In fact, one can study the space of all GX structure on a given manifold M. And the result is that in the neighborhood of a given GX structure, all the other are parametrized, is a local homeomorphism, by their monodromy morphism. And this comes from the following description of GX structure. So given first by Eresman and also discovered by Thurston. It's in fact three equivalent ways to speak about GX structure. The first definition is that of local coordinates in X, but here there are two equivalent definitions. The second one is a flat bundle with fiber X, which of course will come from this morphism, from the fundamental group of M into G. This always gives rise to some flat G bundle, which is trivial on simply connected manifolds. So on the universal cover is M tilde times G. And then you take some suspension here. So you identify two elements mg when the fundamental group acts on the universal cover as deck transformation and on G through the monodromy morphism. So in fact, those morphisms are in fact G-flat bundles. So this will be the G-flat bundle in definition 2. In fact, if you look to the flat bundle with fiber type X associated to this principal bundle, so you make G acts on X by the canonical action, and you will find a flat X bundle. So here is just you replace G by X, and this flat X bundle have a section, which is the developing map. In fact, this developing map, being rho equivariant, means exactly to be a section of the associated X-flat bundle. Moreover, since the developing map is a local diffeomorphism, that means exactly that this section is transverse to the flat structure. You need to think that the flat structure is like a foliation in your flat X bundle, and this section is transverse to this foliation. The third definition is more or less the same, it's equivalent. Once again, you think that your section of the associated X-flat bundle is in fact a reduction of the structural group from G to H. And the fact that the developing map is a submersion, is a local diffeomorphism, means that this reduction is in fact transversal to the flat structure. So those are three different equivalent ways to speak about GX structure on a given manifold and to the space of GX structure on a given manifold. So they are flat structures with this property. So the Cartan geometry will be an obvious generalization of this picture when your flat structure given by this transverse foliation is not always integrable. So you will ask for definition 2 or 3 to be the same, except that this flat transversal foliation is in fact a transversal distribution. It will be integrable if and only if the Cartan geometry is flat. There will be also a more general definition when you also drop the transversality condition. If you drop the transversality condition, you will have something which I will define as a generalized Cartan geometry. And it will also have a curvature. And the most geometric generalized Cartan geometries will be those where the transversality still holds on an open dense set. They will be called branched Cartan geometries. And it will be a broader class of geometric structure. And why we study those structures, maybe I will explain that historically, this was very important in the study of the uniformization theorem for Riemann surfaces. The uniformization theorem for Riemann surfaces says in particular that in fact any Riemann surface admits a complex projective structure. In dimension 1, everything is flat, so complex projective structures are locally modeled on P1 of C, and the developing map will be some isomorphism in between the universal cover of your surface and P1 of C on the round ball in P1 of C or the upper half plane. And the representation of the fundamental group will be inside the group of Möbius transformation, PSL2 of C. So in fact, this was important for the uniformization of Riemann surfaces, and the idea of this talk is to try to have something in higher dimension using flat holomorphic GX structures or even non-flat Cartan geometries. Let me see that what happens. So I will give a definition for now for Cartan geometries, but let's look what happens when H is identity. So in this case, we look to those Cartan geometries which are infinitesimally modeled on a complex Lie group. If you look to definition 3, that means that you have a trivial G bundle. And on this trivial G bundle, you want to have some transverse distribution. A transverse distribution on a trivial G bundle will be something which is a form into the Lie algebra of G. Moreover, the transversality condition, if you want this transversality condition, as in Cartan definition, you will ask for omega to realize in each point an isomorphism between the tangent space of your manifold and the Lie algebra G. In fact, this isomorphism is a vector space isomorphism, and the graph of this isomorphism will be your distribution. Moreover, the distribution will be integrable. The Cartan geometry will be flat if and only if the Lie bracket in M agree with the Lie brackets in the Lie algebra G. So this will give you some curvature. So I will give you the description of compact complex manifold admitting this kind of structure. So this is a theorem of Wang which don't have Cartan geometry, does not have Cartan geometry in the terminology, but it's exactly this. So you assume there is some isomorphism in each point in between the holomorphic tangent space of your compact complex manifold and some vector space of the same dimension. Yeah, it's about parallelizable manifold because, as you said, Misha, just take like EI, a basis, canonical basis of your vector space, and you parallelize your manifold by omega constant holomorphic vector fields. So this gives you the fact that the holomorphic tangent space is holomorphically parallelizable. Moreover, if you take the Lie bracket between two of those holomorphically defined globally vector fields, you will get some other global vector fields, and they split in this basis with some coefficients which are holomorphic functions on the compact manifold, so they are constant. Meaning that those xi, in fact, they have the structure of a Lie algebra of finite dimension. I will call it L. So if you change the structure here of this Lie algebra from G to L, omega becomes an isomorphism of Lie algebra, not only an isomorphism of vector spaces, but an isomorphism of Lie algebras, meaning the structure becomes flat. Your holomorphic parallelization is isomorphic to left invariant holomorphic vector fields of the associated complex Lie group L. And by completeness of vector fields on compact manifold, in fact, your manifold M is a quotient of this associated complex Lie group by a lattice. So in fact, your parallelization must be flat with respect to the structure of some complex Lie group. Your manifold is some L over gamma. And in fact, your form omega must satisfy, if you write down the Lie-Cartan formula, this must satisfy some equation, which is called Morer-Cartan equation, associated to the group, to the Lie group L. So those are 0 because these are constant functions. So somehow you have an equation which is Morer-Cartan equation of the group omega. So moreover, if you stay in the category of Kähler manifolds, you know that holomorphic forms must be closed. So d omega must be 0. So the only structure of Lie algebra which is compatible with the Kähler setting is that of an abelian Lie algebra. So among those palizable manifolds, the only which are Kähler are complex tori, quotient of C to the D with some translation group. Yeah. Yeah, because in fact for Kähler manifolds, holomorphic forms must be closed. So if you look to this equation here, d omega should be 0 because, but this is also omega specialized on this Lie bracket. Now assume you consider that, and this must be true for any holomorphic form. So any translation invariant holomorphic. So take any linear form on the Lie algebra, which does not vanish on this, gives you something which is non-closed. So only on abelian groups, all invariant holomorphic forms are closed. As soon as the group is not abelian, you can cook up some holomorphic one form which is not closed. So let me go now to the definition of a Cartan geometry. So this is Cartan's definition, which was a little bit forgotten because there were some other definition for geometric structure, like rigid geometric structure in Gromov sense, which are maybe easier to handle. But anyway, this was the way Cartan put it, and then it was also worked out by Erasman. You have a holomorphic parallelization, but not directly on your manifold M, on some H bundle over the manifold. So imagine that this H bundle mimic the canonical projection of G over H. So this H bundle is something which reminds you the projection of G over the model. And the form omega is something which reminds you the Morer-Cartan form of G. So now you have this H bundle, which is some abstract principal H bundle, with omega, which trivialize the holomorphic tangent space on the bundle. And you have 3 requirements. The first one, it's an isomorphism, a trivialization. The second one is that, in fact, the third one is the fact that on each fiber, which is a copy of H, omega coincides with Morer-Cartan form on H, meaning that all Lie brackets agree with that of H, the Lie algebra H. Omega is an isomorphism in restriction to each vertical fiber. And the third one is, in fact, that you take one vertical omega constant vector field and any other, their Lie bracket in the bundle is the same as in the Lie algebra of G. Meaning that if you compute this Morer-Cartan form as a 2 form on the bundle, it will vanish if you plug inside at least one vertical omega constant vector field. So this form is basic. It's something which is the pullback from the basis M to some 2 form. And the theorem, Cartan theorem, he was very proud about this, is that this form will vanish, this curvature will vanish if and only if your bundle is locally isomorphic to the fibration of G over H, and your form is isomorphic to the Maurer-Cartan form of G. In the flat case, I will show you, but it's somehow obvious from here, that you will get the GX structure situation. In the flat case, your manifold M is locally modeled on G over H. So we will work also with this more flexible definition, is that of branched Cartan geometry, where in this holomorphic setting, we ask for omega to be an isomorphism on an open-dense set. In fact, automatically, this open-dense set will be H invariant, and it will be the pullback of the complementary of a divisor in the basis. Something like this fails to be an isomorphism on the divisor where some determinant vanishes. So in fact, this open-dense set is the pullback of the complementary of a divisor in the basis. And once again, this branched Cartan geometry will be flat if and only if this curvature computed by the Maurer-Cartan formula vanishes. So why this is somehow more flexible and in the same time rigid enough to work with? So I will give you some explanation. Let's see first that flexibility. In this definition, everything is built in order that your geometric structure is invariant by pullback through ramified map. You can pull back your bundle, and then when you pull back your form omega, you will have some degeneracy of omega, but it's still a holomorphic form. This enables one to have many examples of such Cartan geometries. For example, if you have a complex smooth projective manifold, you, of course, by definition, you embed it in some projective space. And as soon as your embedding is not surjective, take a point which is not in the image and do some generic projection of a projective space of smaller dimension. And you do it as long as your projection on the projective space is not surjective. At the end of the process, you will have some finite map from your smooth projective manifold into some projective space of the same dimension. It's like, meromorphic function on Riemann surfaces. Gives you the structure of your Riemann surfaces as being a ramified map of the complex projective space. So now you pull back the standard complex projective structure of the complex projective space through this ramified map, and gives you the fact that, in fact, any projective manifold has branched, flat, complex projective structures. So somehow, it's kind of uniformization using ramified geometric structure. But of course, there are many of them. So yeah, so I will try to say. Now, what is somehow the rigidity part? The rigidity part is the fact that, in fact, Ehresmann's construction, which gives you equivalence in between the three definitions, works if you drop the first requirement in your Cartan geometry, meaning you drop the fact that omega is an isomorphism. So here what you do is that, once again, you start with your H bundle of your Cartan geometry. So this was done by Ehresmann in the classical case. And you consider the G bundle obtained by extension of the structure group. So you have the same cocycle with values in H and make it act on the fiber type G. Gives you some G principal bundle. And there is a canonical way to endow this G principal bundle with some Ehresmann connection, which I wrote down here. This formula shows pi 1 is a projection of your bundle, so you pull back the Cartan's form. The pi 2 is a projection on G, so you pull back the Maurer Cartan form on G. And this formula is in such a way that everything is H invariant, and this form vanishes on the H orbits, meaning that this is basic. This is something living on this G bundle. It's a form with values in the Lie algebra G, which lives on this G bundle. So here we are in the situation of what Ehresmann calls, what we call today an Ehresmann connection, because the kernel of this form is some horizontal distribution with same dimension as the dimension of M. So you have some kernel. And the Ehresmann theorem is that this distribution given by the kernel of theta tilde is involutive, is integrable, if and only if the Cartan's curvature is 0. So Cartan's curvature 0 means that the G principal bundle admits flat connection. So they are equivalent. And this gives you one of those equivalents in the definition between GX structures and G bundles with connections. And the important remark here is that everything works as in Ehresmann's theorem, even if you drop the condition that omega is an isomorphism. The only thing is that this flat connection, in the flat case, will not be transverse to the fiber type X, meaning that the developing map will not be a local diffeomorphism. For example, in the branched case, your developing map will be a local diffeomorphism on the complementary of the ramification divisor. So it will be a dominant map from the universal cover into the model, which in general is not a local diffeomorphism. But still you have developing maps. And those which are flat on simply connected manifold, they come through ramified map to the model. And now I will give you some results we can prove on those branched Carton geometries. The first results are in the case where the manifold is Calabi-Yau, meaning that we assume that the manifold is compact, Keller, simply connected, and the canonical bundle, which is the bundle of top holomorphic one forms, is trivial. So those are the assumptions on the manifold. And we try to understand branched Cartan geometries on this type of manifold. For example, K3 surfaces are good examples to think about. And we have a flatness result. The flatness result has some hypothesis, which is the following. The group G, which is the symmetry group of the Cartan geometry, must be complex affine, meaning that there is some linear representation in some linear group with a discrete kernel. This will enable us to work with holomorphic vector bundle. We will associate to our G principal bundle some holomorphic vector bundle. I will explain a little bit why this flatness is natural in this context, but let me show a little bit how the corollary works. For example, this will imply that, in fact, all geometric structures on this kind of Calabi-Yau simply connected manifolds are given by dominant holomorphic maps into the model X. They are ramified holomorphic maps into G over H. The first remark is the fact that you need branching divisors. If you don't have branch divisor, the developing map will grow from your simply connected manifold into your homogeneous space, meaning that your simply connected manifold is also a homogeneous space. And homogeneous spaces with a volume form are parallelizable manifold. Because you take, say, holomorphic vector fields which span the tangent space of the manifold in some given point M, and then if you specialize the volume form on those n vector fields, you will have some constant non-zero holomorphic function. It's a holomorphic function by maximum principle must be constant. So you trivialize the holomorphic tangent bundle. So it's a quotient of a complex Lie group by a lattice. It's never simply connected. So that's why, in fact, your geometries need to have some branching divisor if you want to have non-trivial examples. And non-trivial examples you get by the fact that, for example, projective KC surfaces have finite maps into the projective space. So they have flat, branched, complex projective structures.
This kind of flat guys, so is it the list that we gave in the beginning? So what examples like projective structure on CPN is flat?
It's a
and all like other examples that you mentioned in the beginning, they're all flat, right?
yeah,
Right?
yeah.
And these are the one with flat. This was the full list.
No, yeah, good question. So let me answer now. I look to the last point of this slide. The last point of this slide says the following. You have this developing map going from your simply connected manifold into your G over H. This G over H must be a compact space. Now, first remark, this developing map is a local diffeomorphism on an open-dense set. So you can pull back meromorphic function from X on M. And this pullback is injective, meaning that the space of meromorphic function on X injects in the space of meromorphic functions on M. This shows that the algebraic dimension, which is somehow the number of independent meromorphic function on M, must be bigger than the algebraic dimension of your model space. For example, if the model space is the projective space, this implies that your manifold is Moishe-zone. But Moishe-zone Keller manifolds are projective. For example, this characterized among Calabi-Yau manifolds, the projective one, as being the only simply connected manifolds which admit branched complex projective structure. But now I go to your question. For example, this shows that some of them, for example, the complex affine space, the complex Euclidean space, they do not admit such geometries. And for G over P, with G semi-sample complex Lie group and P a parabolic, I don't have complete classification. But our theorem somehow reduces the study to the case of maps from simply connected manifolds into rational manifolds. For the complex projective space, we have complete answer, exactly those which are projective admit submap. But for other flag manifolds or other rational manifolds, I don't have complete answers. Maybe most of the G over P will not be compatible with simply connected Calabi-Yau manifold.
Why is Calabi-Yau necessary for the second part of the corollary? Wouldn't it be true for all Kähler things by the same arguments?
The second part means that if I have
If you have a non-projective.
Oh, yeah, of course. Yeah, you're right.
But yeah, so
the only the point is to prove flatness, and we need Calabi-Yau to prove flatness. Yeah. But after that, once you know that the geometric structure is given by a ramified map, the same argument works. You don't need triviality of the canonical bundle. You're right. But we need triviality of the canonical bundle to prove this. So this is somehow the key of the theorem showing flatness of the geometric structure. It goes like this. By definition, G admits representation with discrete kernel. That means that you can associate to your G principal bundle the linear bundle given by this representation, and the linear bundle will be endowed also with a holomorphic connection. You transport the connection. And the fact that the kernel is discrete means that at the level of the differential, at the level of Lie algebras, this is injective. So if the linear bundle is flat, then the G bundle must be flat also. They will be flat in the same time, because when you compute the curvature, the tensor is the same, except you look to this injection of those Lie algebra. It's a two-form in the Lie algebra. So the linear bundle is flat if and only if the G bundle is flat. So somehow, to prove flatness of a geometric structure, you need to prove flatness of a G principal bundle. So we will prove flatness to the associate holomorphic vector bundle. And why this is somehow expected to be true? So this is a question asked by Atiyah maybe almost 50 years ago. More now. Atiyah made the following observation. You look to the holomorphic, take any holomorphic vector bundle over a Kähler manifold. Assume the holomorphic vector bundle is endowed with some holomorphic connection. Then Atiyah noticed that you can compute characteristic classes first in the classical way. You take any Hermitian metric on E, and then you will have some representative of these Chern classes, which will be a form of type KK on the manifold M. But when you have this holomorphic affine connection on the bundle, you can also compute the curvature of this holomorphic connection, and your K Chern class will have a representative which will be another form which is holomorphic of type 2K0. On Kähler manifolds, this implies that, in fact, the cohomology class is 0. So this was noticed by Atiyah. If you have a holomorphic vector bundle with a holomorphic connection, all Chern class must vanish. So the Atiyah question is, does E admit also a flat connection? Since you don't have those obstruction, does E admit a flat connection?
In case when Chern classes vanish, or
In fact, this proof shows that, yeah, so interesting. In fact, the connection implies that the Chern class vanishes. So you ask this question, but you are right. Question could be asked more generally. Assume the vector bundle have vanishing characteristic classes. Is it a flat bundle? Some answer is known. For example, if you assume that E is the tangent space of a Kähler manifold, then by Yau's proof of Calabi conjecture, you have some Ricci flat metric And since the second Chern class is 0, this Ricci flat metric will have, in fact, sectional curvature which is 0. The second Chern class means that the sectional curvature is 0, meaning that you have some Keller metric which is flat. And by Bieberbach theorem, your manifold is covered by a torus. So in particular, your tangent space admits a flat connection. But in general, the answer is, the question is open. And in fact, we give some answer here when we assume that the manifold is simply connected and Calabi-Yau. CP2 can have okay, so you try to find a bundle which is, yeah, it's not the tangent bundle, but you try to see if there is some answer saying that I have rank 2 bundles over CP2 with C1, C2 equals 0, and they are not trivial. Okay, okay. So, but in fact, I was somehow, okay. But Atia's question is about bundles with holomorphic connections. So I guess your bundles do not have holomorphic connections, yeah. But nice thing, so yeah.
If your bundle is stable, then C1, C2 equals 0 implies that it's flat.
Yeah, in fact, you're right. This is our, our proof which use Corlett and Simpson stability. So if you take a Calabi-Yau manifold and like say projective manifold, if you know that the first Chern class is 0 and the second Chern class is 0, this will imply that somehow that the degree, which is integral on M of C1 wedge the Keller form at the appropriate power is 0, and also the integral of C2. And Misha, you're right. There is a theorem of Simpson saying that in the projective case, it's enough to prove that E is semi-stable. And this is what, in fact, what we prove is that in the projective case, E is semi-stable. And in the Keller case, this Simpson criteria is more involved. You need to show there is some filtration such that successive quotients are polystable of degree 0. But yeah, this is the idea of the proof. And the idea of the proof somehow to prove semi-stability. So let me recall that here we speak about stability in the sense of slopes. So we define the degree, the slope as being the degree quotient by the rank. I assume it's Keller, yeah. Calabi-Yau.
Then it's stable, it's polystable by
the tangent. But here it's not the tangent. You're right. The tangent is stable, but here you have any vector bundle. This is the point, any vector bundle. So, but you're right. So in fact, semi-stability means that if you have F a subbundle or a subsheaf, then the slope must be smaller than that of E. And now the idea of the proof is to assume that E is not stable. Then you take W maximal destabilizing subsheaf, and you show, in fact, that W must be invariant by the connection. You show that the second fundamental form must vanish, and it uses your argument about the polystability of the tangent space. And you know that this maximal destabilizing subshift is invariant by the connection. Now, then you show that some subshift invariant by the connection is locally free, is a subbundle. But if it's a subbundle, Chern classes of this subbundle, first Chern class must be 0. The degree is 0. And since also E has a connection, the degree is also 0. So it's not destabilizing. So this is the proof in the projective case. And somehow this is also interesting to notice that a TIA question has some limits in the fact that if you ask the same question for principal bundles, you have elliptic bundles over projective K3 surfaces which admit connection, but the bundle is not trivial. So it's not a product. They do not admit flat connections. It's a non-Kähler situation. And this can be constructed by starting with a 2 form on a K3 surfaces, which has periods in a lattice. And then this lattice enables one to construct this elliptic bundle in such a way that primitives of these 2 forms are connections on these elliptic bundles, and their derivative is these 2 forms. So they are, and the bundle is not trivial. It admits these non-closed holomorphic 1 forms. It's not Kähler. So that's why we need this complex affine hypothesis on the Lie group G. It cannot work for any group. This remark was told me about Marco Brunel. He showed me how to construct. It was in his work of how to construct non-closed holomorphic 1 forms on non-Kähler, of course, manifolds. In fact, maybe an easier example, but which is not simply connected, is to look to the Heisenberg, complex Heisenberg group, quotient by the Heisenberg subgroup of Gaussian integers. And this will be an elliptic bundle over 2 torus. And this elliptic bundle over the 2 torus also admits this kind of holomorphic connection, which is not flat and does not admit any flat connection. So here it's an elliptic bundle over K3 surface. The basis is simply connected. In fact, a TIA question also inspired the following question, which is about Cartan geometries. If you have, say, simply connected manifold with a model G over H, the question is it true that in fact your manifold also admit a flat connection? A flat connection with the same type. This would imply that your M is biholomorphic to G over H. For example, this conjecture, and once again, the previous results go into this direction, because Calabi-Yau manifold, if you have some geometry on this, some G over H, then you are isomorphic to G over H, and G over H do not have trivial canonical bond. Also, this conjecture is open even for the complex affine space. We do not know if simply connected compact manifolds in general could admit complex affine connections in the tangent bundle. Of course, it's true for Kähler that they are covered by a torus. But in the non-Kähler setting, this is open. I will give you some results going to the direction. And another nice geometric situation is to think about the model which is the complex projective space. This conjecture would say the complex projective space is characterized as being the only compact, complex, simply connected manifold with complex projective structure, complex projective connections. Of course, with a flat complex projective structure, it will be the projective space. The developing map will give you isomorphism, but assume it's non-flat. Can we characterize those which admit complex projective structure as being the complex projective space? So I give you some results going in this direction. The first one is you assume the manifold is scalar. It's slightly more general. It suffices to be bimeromorphic to a Kähler manifold, to be in the Fujiki class C. And you assume your Cartan geometry is algebraic. For example, G over H is a rational manifold. Then the manifold must be projective. And this is somehow infinitesimal version of Borel-Remer theorem. Because by Borel-Remer theorem, if you have a homogeneous space, compact homogeneous space, it's a product of a rational manifold with a complex tora. If, moreover, you are simply connected, there is no tori. So you are a rational manifold. So you must be projective. Simply connective, Kähler, homogeneous manifolds are projective. So this goes into this direction. So if you have this kind of geometric structure, you would like to say that your manifold is some algebraic manifold, G over H. You say that M is algebraic. Also, if you think about connection, we have these results that your simply connected manifold do not admit holomorphic Riemannian metric. This is somehow less general than connections, because let me give you the precise definition. The precise definition is that your holomorphic Riemannian metric is a section of the square of the second power of the second symmetric power of the cotangent space. So in each point you have a complex quadratic form which is non-degenerate. It realizes something like this, an isomorphism in between the tangent space, holomorphic, and the holomorphic cotangent space. So gives you also the fact that canonical bundle is isomorphic with the anti-canonical bundle. Meaning that the canonical bundle is of order 2, and on simply connected manifolds, this is exactly like in Riemannian geometry. You have some volume form which is defined up to a double cover. And on simply connected manifold, this implies that the canonical bundle is trivial. And moreover, you have also a Levi-Civita connection. You have a holomorphic connection, unique, which is torsion-free, and for which this tensor is parallel. So if you have this kind of structure, your manifold must have infinite fundamental group. You cannot be simply connected. So I will show you a little bit why this is true. And a last result with Biswas and McKay show that if your manifold do not, if the manifold is of algebraic dimension 0, so the only meromorphic functions are the constant ones, and moreover you are simply connected, you cannot admit this kind of Cartan geometry of algebraic type, because once again you think that if it's flat, your manifold will admit some dominant map into this algebraic space, G over H, and you pull back meromorphic functions through the developing map. So the point is to show, and this is part of the result, the first step of the proof is to show that if you have this kind of Cartan geometry, your compact complex manifold must be something which looks like a torical variety, meaning this will be a complexification of a complex abelian Lie group, equivariant compactification of a complex abelian Lie group, And on those equivariant compactification, we show that all branched Cartan geometries must be flat. We use this action, which is almost homogeneous, to show that the curvature must vanish. So those are kind of results we are able to prove in the direction of the characterization of compact simply connected manifolds with those kind of Cartan geometries. And let me show what kind of tool can be used here, for example, for those holomorphic Riemannian metrics. In fact, the result is very natural for the following reason. The first fact is the following. Look to this isomorphism between the tangent space and the cotangent space. Assume there exists X, a section of the tangent bundle, then the dual form will be a holomorphic one form on the manifold. If you are able to prove that this holomorphic one form is closed, you are done. Because closed one forms are never exact. They would be differential of some holomorphic function, which must be constant. So you have some non-trivial element in H1. So the abelianization of your fundamental group must be infinite. So the point here is to be able to construct first holomorphic global vector fields on those manifolds, and second, to prove that the dual form is closed. How you can construct those kind of vector fields? So the step one is how to find global holomorphic vector fields. In fact, you find even killing vector fields, those for which the flow preserves the geometric structure. And in fact, here what is important is first, by a Nomizu result, local killing fields for G extend to global killing fields. So it's enough to find some local symmetry. And now, how one can find local symmetry for those holomorphic Riemannian metric? This follows a method coming from Bogomolov and Gromov. To find local symmetries, you do the following construction. You have your manifold M, and you look to the frame bundle over M, which is some principal bundle with orthogonal group as structure group, the stabilizer of the complex quadratic form. And you compute, think that, in fact, for manifolds with holomorphic Riemannian metric and with connection, you have exponential coordinates, meaning that as soon as you have a frame bundle, you have local coordinates on your manifold, exponential coordinates uniquely associated to this frame. And in this frame bundle, you look to jets of the metric, K jets of Riemannian metric. So this is like a space where the first jet is the standard quadratic form. Then you have some linear part, which is 0. And then you have some quadratic part. And the important thing here is this is like a K-jet of your metric. And this map is equivariant. The orthogonal group will act on the space of jets of metric by linear isomorphism. It will fix this point, the linear part 0 and the standard quadratic form. And on the associated linear vector space, it will act in a linear algebraic way. And the point, the rigidity of Riemannian matrix, and it works for any geometric structure that Gromov calls rigid, show in fact that for K big enough, you have the following picture. M and M prime points in M are related by a local isometry if and only if the image of this K jet of the geometric structure of the fiber over M is the same orbit in the space of jets as the fiber of M prime. Meaning that if, for K big enough, if you have the same K jet in two different points, they are related by local isometry. The second remark is that since you're yeah, some universal constant for a compact, yeah.
Or it depends on the manifold. Should be something like 2 or 3, I think. If it's
No, it's more than 3 because 2 you can find, curvature, homogeneous manifold, but it's something which depends on the dimension of the manifold. It's universal constant with respect to the dimension of the manifold. The first kind of these results were proved by Singer. So you need to have some curvature and some derivatives of the curvature which are in the same orbit. And the point is that now this space, you want to understand the orbits of the orthogonal group in the space of jets of matrix. And here you have theorems like Rosenlicht theorem saying that orbits of an algebraic group in generic position can be separated by rational functions, by invariant rational function. Meaning that if M and M prime are not like this, you can construct a meromorphic function on the manifold M which separates this point. For example, for manifolds of algebraic dimension 0, this will show that you are locally homogeneous on an open dense set. So you have many local killing fields going in all directions. Moreover, they extend by no means. So they are your manifold is almost homogeneous. And moreover, this works for any geometric structure. So you put in your geometric structure also those vector fields. So the centralizer of this Lie algebra of killing fields also acts with an open dense orbit. So you have a space which is an almost homogeneous space for an abelian group. And on those spaces, all forms are closed because, you look to d omega x g, and the formula will say, Cartan formula will say that this is 0. Those are constant functions, is 0, and the algebra is abelian. So on compactification of abelian Lie groups, all one forms are 0. All one forms, in fact, are closed. But since you are simply connected, you don't have forms. So it gives you the contradiction you were looking for. You have many global vector fields, and all of them will give you forms which are closed. And in general, if your algebraic dimension is not 0, you have the following situation. You have some bimeromorphic model, which is like this, your manifold M, fibers over some basis. This is the algebraic reduction. The basis is Moisheson manifold, and the meromorphic functions are on M are pullback of meromorphic function on V. Meaning that if you have this kind, and let's say that here the algebraic dimension is D, shows you that in fact, like here, you will have killing vector fields acting transitively on the fibers of the algebraic reduction. And if you plug inside the volume form those vector fields acting, let's say, n minus d, let's do something like this. You take those holomorphic one forms, which are dual to those vector fields, and you show that they vanish on the fiber of the algebraic reduction. So they are basic. They are pullback of forms which live on a Moisheson manifold. But on Moisheson manifolds, the forms must be closed. So you construct in such a way closed forms, closed one forms, or your simply connected manifold. And this is a contradiction. You also need to do something to show that those forms vanish on the fibers of the algebraic reduction. And for this, you prove something like this. If the automorphism group of a holomorphic Riemannian metric or a pseudo-Riemannian metric is non-compact, then there exists a local killing field vanishing at a generic point on M. This is Poincaré recurrence theorem. You have the automorphism group of the geometric structure. It preserves some finite measure, so you have some recurrence. And if you have some recurrence in your manifold, you are able to construct non-trivial, non-compact isotropy, meaning that those vector fields will vanish somewhere. So when you specialize on any other global vector field, this will be 0. And this will vanish on the fibers of the algebraic reduction. And another argument here is to show what happens when your manifold is Moisheson, because this theorem of Rosenlicht will not give you local symmetries if the manifold is Moisheson, because meromorphic function will separate points. But for example, in this case of holomorphic Riemannian matrix, in fact, you have something like this. It's more general, but it holds for any Cartan geometry. But if Tm, the holomorphic tangent bundle of a manifold, admits a holomorphic affine connection, this implies that you don't have copies of P1 of C into M, which are non-constant. You don't have non-constant rational curves in M. And this is very easy. You take the differential going from the tangent space of the projective space to the tangent space of M restricted to P1 of C. But if you have a holomorphic connection on the tangent space, in restriction to P1 of C, it will be flat. So the tangent space of M in restriction to P1 of C is a trivial vector bundle. And this one is positive. So you don't have non-trivial morphism here. And if you don't have rational curves in a Moisheson manifold, your Moisheson manifold must be algebraic. So Calabi-Yau, and we've seen that Calabi-Yau manifolds with holomorphic connections are covered by tors. So those are some elements of the proof for the theorem of holomorphic Riemannian metrics. For the second theorem with Bisbas and McKay, let me say the following. So theorem 2, once again, algebraic dimension 0 and simply connected manifold. Assume by contradiction the manifold is simply connected. If M admits a Cartan geometry. And this algebraicity condition is exactly what we need to apply this kind of methods of Rosenlich theorem, since once again we look to the Cartan geometry and to derivatives of the curvature. So we have some representation of the structural group H into the space of jets. And we assume this is algebraic. So once again, if you assume the algebraic dimension is 0, M admits a Cartan geometry which will be locally homogeneous on an open-dense set. And once again, you can put together in the geometric structure all the symmetry vector fields, they globalize, give you the fact that M is a compactification, equivariant compactification of a complex abelian Lie group, typically C star to the n, which is somehow a non-algebraic version of torical varieties. And step 2, on those compactifications, all branched holomorphic Cartan geometries are flat. And once you prove this flatness, you have this developing map going from M into this projective manifold, and you pull back meromorphic function, and you have some contradiction with the fact the algebraic dimension is 0. And to prove flatness, somehow, once again, you use the fact that on abelian compactification or complex Lie group, all, let's say here, this formula shows that all one forms are closed. But your manifold is simply connected. So in fact, you don't have one forms. And you don't have two forms, because if you have a two form, you plug inside one of those holomorphic vector fields, it's almost homogeneous, gives you a one form. So you don't have, in fact, K forms. You don't have forms. Now, also, if you have E, a holomorphic vector bundle with a holomorphic connection, the curvature will be a form. So the holomorphic connection must be flat. So this will give you degree 0. And once again, you have these stability conditions showing you that E will be semi-stable. And you apply this for the adjoint bundle of your geometry. And you show that the curvature will be a two-form curvature of the holomorphic Cartan geometry. It's a two-form on your manifold with values in this semi-stable vector bundle of degree 0. And once you plug inside holomorphic vector fields, give you non-trivial morphism from the tangent space of M into this vector field, into this semi-stable holomorphic vector bundle with degree 0. And you show, in fact, that any quotient of a holomorphic tangent space by a subshift must be of positive degree because of this condition. So this gives you the vanishing of the curvature. So in fact, in these results, you have some mixing between arguments coming from differential geometry and also some semi-stability results for holomorphic vector bundles. But once again, they go into the direction which would be, let's show that, like in Attia's question, if on a simply connected manifold you have a Cartan geometry, you will also have a flat one, so you can classify those manifolds. I will stop here. Thank you.